Okay, as promised, we're going to add a little more detail to our discussion of how we do uh, texture mapping in WebGL. It'll also open up some new options for you, and we'll wind up actually looking at some code as we go through this. Okay, so first thing we want to do is look at texture objects. Like many other things we've seen, like vertex buffer objects and others, texture is now handled as an object in the very same way. The importance of this is that originally there was just one active texture, and if you wanted to change the texture, you went through setting up the texture all over again and setting all the parameters and actually reading in the image again. You'd have to do text image all over again. And so it was very, very slow. If you imagine having an object where each surface has a different texture map to it, it would be terribly slow because you'd be constantly redefining your textures. What texture objects let you do is store multiple textures and all their parameters on the GPU, and now switching between them is just another execution of a bind operation, this time for texture. So it was an enormous advance. It's very, very straightforward to implement. It'll look very much like what we did with vertex buffer objects. We'll see a few more of the parameters in this lecture. In particular, we'll be looking at how we do MIP mapping and a little bit on, I'll just show you an example of using multiple texture units, and we'll look at the code, what actually goes on in particularly the fragment shader, and how do we couple those variables back to the texture generation that was done within the JavaScript file. So let's start with a texture object, and let's see what we have to do. So the things we have to put in there is not only at the end we're going to actually put in the image, but we also have to say a few things. There are a lot of filtering options that'll enable us to get rid of, or at least ameliorate the effect of aliasing by smoothing out the textures. We want to set how the textures are wrapped once we get outside of the 0-1 range of the texture variables. The perspective correction hint is now kind of automatic. It turns out that the kind of interpolation that was originally done on texture coordinates, particularly by the rasterizer. See, all this is kind of being done automatically now. Worked okay. You did what was called bilinear interpolation, but that turns out does not work quite right under perspective viewing, and there was hardware corrections that made this interpolation work for perspective views too. This is kind of automatic now, so I probably should have left that out, but it's important to note that the interpolation schemes are taking into account that you might be doing a perspective view. Then we do a bind to say this is now the present texture object, and if we have to do enabling, we'll do enable that and select the active texture. And then on the application side, in the JavaScript file and with the definition of the polygons, we're going to set the texture coordinates as we talked about in the previous lecture. We also can use the shaders, and there's an example I think in the book of doing that, and I won't be talking about it here, is that we can also generate the texture coordinates. Since it's just another attribute that's being passed along, there's no reason why you couldn't set the texture coordinates directly within either the vertex shader or the fragment shader and get a much more flexible mechanism for doing texture mapping. Okay, so let's start by looking at some of the parameters. So the one is that we're going to say, what do we do if S and T, the texture variables, are outside the 0-1 range? How do we do averaging? Really, we're going to have two primary choices in WebGL. We're either going to do averaging of some local texture values in the neighborhood of the texel we're working with, or we're going to do what's called point sampling, where we just take the closest value of a texture that we can find. We'll talk about MIP mapping here. There's environment parameters which actually are fairly limited within WebGL, but the idea is that you want to talk about how the texture map, the texture image, interacts with other things you may be doing, such as lighting. And that's really totally free because you're going to determine that yourselves by how you write your fragment shader. So a lot of those parameters that used to be here and are still in desktop OpenGL are really not needed within a shader-based environment because you can do that and many more things that were available with those parameters. Okay, so the first thing is, what do we do if the values of S and T are either below 0 or greater than 1? How do we get a texture value? Well, first we can set those independently. So the function we're going to use for all of these things we'll be talking about for a few minutes here are the function GL text parameter I because it's an integer. And we're going to set it to one of the available options, which are defined within the OpenGL or WebGL context. So a couple of things we can do is, one is we can do it modulo 1. So if we have a value like 1.5, it'll be mapped into 0.5. Negative values will be also evaluated modulo 1. That's called repeat, that the textures then repeat as S or T get bigger than 1 or less than 0. And that gives you something like this. So if I had a texture here on the bottom left, again a little checkerboard, by just repeating that texture I can generate checkerboards at higher resolution by just playing around with the S and T variables. Now you may not want to do that. You may want to wrap them around, and so that's the wrap. It's the wrap parameter, and if you just want to have it clamped at the end, so this thing kind of GL repeat, what it does is now evaluate modulo 1. What clamp does is say just take the value at 1, and if I give you a value of S or T greater than 1, then use the value at 1. If I give you a value less than 0, use the value at 0. So here's a little example of what clamping does when the values are outside the range. You can see here it's outside of the range in one of S and T, up here and up here, but not the other. Up here it's greater than 1 in both S and T, and so it becomes the value at this corner, which happens to be black. So you'll want to set those yourselves, or if you know that parameters are between 0 and 1, then you don't have to. Well, actually, I'm not certain of this. I forget whether you may have to set at least one of them. If you try commenting out some of the lines of code in my examples, you'll see whether you have to set these parameters explicitly or not. Now, next thing is called magnification and minification. The question is, how does a particular texture, or in particular a given texel, map to a polygon, a triangle that you're trying to render? Now, these examples I've drawn as little square polygons, only so it looks a little easier. In practice, we're going to break those into two triangles. But the idea is this: what happens under magnification is that this single texel actually gets spread over a bunch of pixels on the display, and in minification, one single pixel, multiple pixels correspond to a single texel, and that can cause some real jaggedness. So, for example, in magnification, if you're plotting, if this were, say, this green pixel was green, and you colored it all green here, and then this color was all white because of these surrounding texels are white, you're going to see the jaggedness in the display, and you may want to smooth that out. And so you can decide independently how you want to handle magnification and minification. And really the options that you have in WebGL are somewhat limited in either you pick the nearest texel when you're doing the sampling. So if I get the texture coordinate says for here the nearest texel is this green one, I'm going to put green there. But if I'm near an edge, what it's going to do is take a little, if I select linear filtering, it's going to take a little 2x2 region and average out those texels. So if I average them out for some point over here, I'm going to wind up averaging over these four texture values to get a value over here that'll be somewhat of, in this case, of a lighter shade of green. So we set those again with GL text parameter, and we'll see that here in the next slide. Nearest means point sampling, and linear, this should be a little GL dot. Linear is linear 2x2 filtering. Nearest means to do a point sampling. So again, we do GL texture 2D. We can set a mag filter and a min filter separately as either linear or nearest. In desktop GL, you have some other values. There used to be a real time penalty for doing this. In modern GPUs, there's no penalty for doing linear filtering. It's just what you find visually better. And in a minute, I'll give you a little example showing you some of these options. Now, they get combined in various ways, up to you, with MIP mapping. So remember, MIP mapping allows us to have textures at various resolutions so that we can be much more efficient by, if something is going to project into a small area, we don't want to put a high resolution texture on it, because that's all going to get averaged out or sampled in the rendering process. So as we define the texture images, we can use the level parameter here to say which one it is, where 0 means the highest level, 1 means that you're cutting it in half. So if you had a 1024 by 1024 for level 0, level 1 will be 512 by 512 and 256 by 256. Now you have to set those things up yourself. So it actually can lead to some really interesting things you could do, where you could say, well, gee, if I'm down at a lower resolution, I'm going to display one thing, maybe a very simple thing, but maybe as I go to a higher resolution, I blow it up and I can see what's inside. Or you could write a very simple function that takes a given texture at the highest resolution and simply creates the textures at the half resolution. So you'll get smaller errors, although you're trusting WebGL to then make the decision, or actually the GPU, to make the decision about when to switch between a texture at one level and a texture at the higher or the lower level, and you'll see that in the examples I'm going to show you. Now you can also combine these with the filtering options. So you can have MIP mapping and point sampling, MIP mapping and filtering. You can have just filtering, just MIP mapping. All those combinations are possible, and thereby selecting different values of the parameters. So I'll show you that. Let's look here. This one probably is the image that's in the book, but it probably doesn't come out as well because there's another various levels of sampling that occur when you do the book, because that's digital. It's taking my digital image and you're getting all kinds of array-like effects, and you could see that up here in all of these. So it's hard here to see on my screen, at least. I don't know what's going to be recorded on the video, to see the differences between these examples, but I'll show you that separately. There's an example on the website that's called Texture Square that allows you to pick the options and play around with this, which I'll get to in just a second. But here's some of the examples. You can do point sampling, which is the simplest thing. As I said, now the difference between point sampling and linear probably is no difference in time, although visually you'll see differences. Here's doing MIP mapping with point sampling and MIP mapping with filtering. So let me show you a different display of that, and let's fool around with that program on the website. So let's go to here. Okay, here we go. So this is a program called Texture Square. It lets you, I made it as big as possible for this display. So you can, what it started with is a single, this actually started as a square in space, 3D space, and I let you move the viewer with a similar kind of interface as we had here, changing the near and far planes, and here's the important one. I'm changing the aspect ratio, because what I want to do is maximize the sort of the convergence in the distance, so it sort of looks like a trapezoid. But in fact, if you look at the code, this is a checkerboard mapped onto a square. And here's some of the options over here. You can select which texture option you prefer. So here's nearest sampling, and I can see very clearly, and I think you should, the moire effects or the beating patterns that are one indication of the aliasing, and you get these patterns which are kind of pretty here, but they're really annoying to look at. The other thing to notice here, in contrast to the linear filtering I'm going to show you, is that the edges, though, are very sharp, but you probably can see some of this jaggedness along the edges down here at the bottom because you're not doing anything to counter the aliasing. There's no filtering occurring here. Now, if I switch to linear, okay, let's do that. Notice that back here, it's a little bit better. You're not getting quite as much of a beat pattern or moire effect, but down in the front here, you've got rid of the jaggedness, but the expense of getting rid of the jaggedness is things have been smoothed out so they appear a little bit fuzzier down over here. Now, if I combine that with MIP mapping, so here's MIP mapping with linear, with point sampling, and that's kind of neat because notice it's much smoother as you go back here to getting into where the checkerboards are closer and closer on the display. It's a lot better than what you had. Let me sort of switch back and forth. I think it's a lot better than what you had over here. You see that effect is really been reduced, but you still got some patterns over here. At least I'm seeing on my display in the middle, and I could really notice the jaggedness here. That there's a lot of jaggedness on these black-white transitions, and this is a pretty good example here. If you fool around with these parameters up on top, you can probably get different patterns and maybe see more distinctly where it's switching between levels of the MIP mapping. There's one occurring over here, there's a couple occurring over here. That might be clearer when we do linear filtering with MIP mapping. And actually, that's a very nice display. See, now look at what's happened here. You've sort of blended it into the background by doing the MIP mapping. So this should be a lot faster to implement. But because it's linear filtering, notice that you're getting a very much smoothing here. The jaggedness is gone, but it is blurrier down over here. Let me try one thing here. See if we can do that. If I change the aspect ratio, whether you can actually see where, now it doesn't really come out to see where the transition is occurring between the MIP maps. But if you play around with this a little bit more, I think, let's see if this does anything. No, that's not helping. And let's see if I change the near plane. That's changing a little bit. There's really a delay here. This one you can see a little bit better perhaps where, oh well, that's too far. Here you can see a little better where the transitions are between the map levels. So play around with this, play around with some of the parameters in the code, and I think you'll get a better feeling for how texture mapping is actually applied. And it's certainly having checkerboard images really accentuates the visual aspects of aliasing. Okay, so let's go back to the slides, and let's go on a little bit. Okay, so how do we apply the texture? This is again what you'll determine in your own fragment shaders. But there's three options that used to be specified within the fixed function pipeline, and those functions have been deprecated because they're easy to program in yourself. So one is that you let the texture fully determine what the color is. So you're just going to set. We're going to talk about a sampler in a few minutes. The texture image totally determines the color. That's what it's sort of like what's sometimes called decaling, where you like paste a label onto something. More realistically, you might want to modulate it with a color that you computed, for example, by lighting, and that would that's a nice option. You just send all the same parameters over to your shaders and compute the color from lighting, and then combine it with the color from the texture. You can also combine in certain circumstances. You can blend it together with what's called an environmental color to give it a certain shade or feeling that can give you a certain kind of lighting effect. The modulation is often used as a way of creating effects that are more like colored glass, and things we'll be talking about more, layers of colored glass, which we'll be talking about more when we talk about compositing in sometime next week. And we could also use multiple texture units. I'll give you an example of that in a bit, where the idea is that you can apply texture after texture. So we have physically on the GPU, there are a sequence of texture units, texture unit 0, texture unit 1, 2, so on, and there's a certain minimum that has to be supported. So you can apply texture 1, then apply texture 2 on top of it, texture 3 on top of that, and so on, and that makes it lets you create some very different effects and make certain other effects much easier to accomplish, and they're set up within just we set up a texture object for each unit, and then within the fragment shader you apply all of those different textures in order. Okay, so other things you can do is you can start with you can talk about an environment map. That's a texture. So when we were talking about maps last week, or we talked about, oh no, actually we're going to be talking about them next week, is we can map an environment onto an image. We at least saw a slide showing that. How do we get that image? Well, we can do it by either scanning or getting a camera and taking a picture of the environment and then using that as a texture. A really nice example is using a cube map, and I'll give you some examples of cube maps next week. Multi-texturing, as we said, is just applying a sequence of texture units. It's also a way of creating some effects and also reducing anti-aliasing in your image. A lot of that is not quite yet available in WebGL, but we're going to be seeing it. And once again, you can do an awful lot yourselves within your fragment shaders. Okay, so how do we actually apply the texture? We haven't talked about that. We said, well, where's this actually happening? All we've done so far is look at a code that sets up the texture object and also provides the image and tells the system what the size of the image is and what its format. But we haven't talked about applying it. Well, it turns out applying it is really, really simple. There's an additional type of variable that we use within the fragment shader that's called a sampler. And it does exactly that. You give it some texture coordinates and it goes to the texture image and gets you a sample of that texture image. And it's a uniform variable. It's set up within the application file and then passed on when the information is passed on. Basically, you're passing on the texture object, the fragment shader, and then every time you need a value, all you do is give it the name of that texture object and the texture coordinates you wanted to apply. For a 2D, there's only two options supported in WebGL: 2D texturing and cube maps that we'll talk about next week. So this is it. This is how you get the texture. If you want the texture to fully determine the color, then you just set frag color equal to the sampler value that's returned. If you want to also use the color that you computed, here I'm assuming the color has been passed on from the vertex shader. In some way, it was either determined in the application, sent to the vertex shader, and then passed on. Here they're multiplying together, but I can do anything I want here. I could put any function I want here, add them together, do anything else. So it's very, very easy to apply the texture once it's been set up. What about the texture coordinates? Well, generally what you're going to do is when you set up your vertices, their positions and their colors if you want, you also set up a texture coordinate as another attribute. So as far as the vertex shader is concerned, there'll be something we'll call vtext coordinate that is sent over from the application as just another attribute. It's then the most likely case is you're going to output that to the rasterizer. And that'll come into the fragment shader as a varying variable, and this will be the text coordinate that we're actually going to apply. So it's very similar to everything else we've done. The only complexity might be setting up how you're going to determine those texture coordinates in the first place and specifying all the parameters that you need to specify. So here's again the checkerboard image. This is the same example that we used in the last lecture, just saying, hey, here you can set up an image in your own code. You can now, here maybe this makes a little more sense. Again, this is the same slide as in the last lecture, where we now also define the texture coordinates here. This is for the cube example. We now put a texture coordinate into a separate array corresponding to each vertex's location, and if we have a color, we also put that in a separate array. The additional code we need is the code that now sets the texture object. and here's setting a texture object. I tend to put these things in separate functions so the code is a little cleaner. So we do a function called create texture that incorporates most of this stuff within it. So configure texture, excuse me. So configure texture is a function that we'll call, we pass in the image, either the image that's defined by something like a GIF file or a JPEG, or the image that we computed as previously with the, see, here's one way of calling it. It's called image1 here. So I would now do in my JavaScript code, I'd execute on load, I'd configure texture of image1. Okay, so how do you do that? Well, here's setting up the texture object. Here's the detail. I create a texture object by the GL create texture, just as we did with other attributes. I bind that texture object. Now it's a bind texture instead of just a bind vertex attribute. This line here is for the example where I use the icon, that image from SIGGRAPH. And what we had to do is do the same thing we talked about when we talked about input. I have to flip it. So there's an unpacking operation that has a parameter called unpackFlipY WebGL, which just says take that image, which WebGL understands, and flip it over because the parameter is set to be true. Okay, here's the setting up the texture 2D texture image. It's a RGB image for that example. It's an unsigned byte, and we just do a pointer to the image the name that's been passed in. Now, in this example, I'm using MIP mapping, so I can actually generate all the MIP maps automatically. It has the image. I just execute the function generate MIP map for 2D textures, and it's being generated. Okay, it's a little annoying to put that texture 2D in here all the time because that's basically all that's really being supported. But on the other, it's a legacy kind of thing from older versions, and they decided not to take it out. Okay, here do we set up the parameters. In this case, I'm using for min filter, I'm using mipmap linear. For the mag filter, I'm using saying just take the nearest. And now I say which is the active texture unit. I remember we just talked about having cascading texture units. I'm saying the one that this texture is going to apply to is texture unit 0. Okay, they're numbered texture 0, 1, 2, and so on. And now I send all this information over as a uniform 1i. It's an integer, it's one-dimensional. I send that over. First I have to get the location of that parameter from my program object, which we assume has already been compiled. The name texture is the name that's inside of the fragment shader that I'm using, and 0 refers to texture unit 0. So now this is setting up the whole texture object in here, and now I have to do one more final thing, which is to link that together with the shaders, but it gets linked exactly like everything else. That I set up the texture coordinates as exactly as before as a vertex attribute. I get its location. I enable that particular variable. I get a pointer to it. I say it's two-dimensional texture. The values are floats. S and T are going to be the texture coordinates are going to be floating points. I don't want it to be normalized, and so it appears just like what we had before. There's no offsetting going on here. And now what I'll do is just send that uniform over. This is again just the line of code in the previous slide where I'm sending it over to texture unit 0. And that's pretty much all that's involved. Let me show you finish up today by showing you one or two very, very simple examples. Again, these examples are all on the website under Chapter 7. Okay, so let's see if I can get to those. Okay, here let's get back up for this example. And let's look at, here again is, here's the cube example again, using, okay, so here it is. This is the example where the color is multiplying the texture value. It's pretty much what we had on the slide a few minutes ago. Actually, this example pretty much has the same shader. Here's texture cube 1. This is essentially the same example where the color that I pass on as a vertex attribute is multiplying that texture. So these two examples we've seen. I want to show you just two more here. 3 down here, yeah. This one looks the same, but what I've actually done here is use two textures. What I've done is make one texture be all the rows of black stripes, and the other one is the columns of the black stripes, and I get the effect of this much denser checkerboard by multiplying those two together. So take a look at this example when you can. And a similar example is this one, 4 down here. Yeah. This one I kind of like. This is using two texture units. The first unit is applying the cubes, the checkerboards to the cube. So that's why you see this black and color pattern. Again, the color that I'm passing in is multiplying the texture value. But I've actually now employing a second texture unit, which does a two-dimensional sinusoid on top of the texture that I already generated. So now you see these kind of interesting patterns being superimposed on the first texture. So it's just there to give you an example of just how much you can do with textures, and again, repeating myself multiple times. You have tremendous freedom within the fragment shader to do things. And over the next week, we're going to be looking at a lot of applications of texture mapping to things like image processing, to agent-based models, various things where we now combine these texture techniques with the idea that we can now render to an off-screen buffer and bring that back as a texture map to use in the next rendering. And all of that we're going to see next week.